So today we will discuss one of the most important theorems in the theory of ordered systems and theory of phase transitions, if you wish. This is the famous So this theory deals with systems possessing continuous global symmetries. A typical example being isotropic magnets, for instance, where the spin vectors of magnetization can be rotated freely. The global vectors of magnetization can be freely rotated on the surface of an imaginary sphere, and nothing changes. All those states are completely degenerate. And as a consequence, as you already know, there exist excitations with a linear spectrum. Well, I wouldn't say always with a linear, with a spectrum such that the energy of these excitations vanishes in the way a long wavelength limit, the limit of k goes to 0. Generally, for most of the systems, this dependence is quadratic, is linear, but there are exceptions, like such as ferromagnets, when the dispersion is quadratic. We'll discuss maybe at some moment this difference. So for us, what is important, so let us consider the case when the other parameter is the magnetization, which is a n-component vector. N-component vector. So it is assumed that at some temperature below the C, this vector takes a non-zero expectation value, called that naught, which can be measured, which can be calculated. And this signifies that the system undergoes a transition to an ordered state with non-zero spontaneous magnetization. Of course, we assume that this vector is the main order parameter field of some functional of the free energy, and that free energy is invariant under ON transformations. Transformations, more typical transformation would be, as I once said, MI, that goes to M on I, which is R I K, and K, and the matrix R is orthogonal. Orthogonal real matrix describing belonging to the symmetry group O, and basically its proper rotations are included, of course. But apart from proper rotation, there are also reflections. We don't talk about this. So you may ask how to describe the transition. Well, within the mean field we can do that. If we simply define the free energy difference, which is the free energy of our magnetization field, minus its value in the paramagnetic phase when M is 0, then typically what is written here is the space can be of any dimensionality ddx, and here we have the gradient term. Okay, I have to be careful here. Let me sum over 1, 2. Okay, it depends on the choice. How should I? Yeah, let it be like this. 1 to n. And this will be the component of the gradient times the vector itself. And then I have another term, m squared No, this is not good what I wrote. I'm very sorry. Oh, this is terrible what I wrote. No, it should be D, of course, because these are the components of the gradient. The gradient is the gradient delta is ddr dx, and therefore it represents a vector ddx1, ddx2, as many components here as the dimensionality of space. So there are two actually spaces. One is the space of degeneracy of the other parameter, right? Which is uncomponent. It's nothing to do with real space when coordinates leave, right? When the lattice is deformed. So the gradient goes with respect to. So to be quite honest, I would have written something like this: delta alpha mi squared summation over alpha from 1 to d summation over I from 1 to n. This would be exactly how it should be written, I would say. Right? It's a tensorial structure, so I'm summing over all alpha, over all spatial components, and I'm summing over all components of magnetization. But these are being summed within different manifolds. This is a example. The idea here is that don't be confused, right? The x vector and m vectors, these two vectors live in different spaces. Right, okay. It's an origin of confusion. Even when I look into my old notes and prepare for, even for the lecture, today I always get confused. I is just labels the component of the vector, or labels the coordinate axis in real space. So this is this term, and there is one more term, 1b. It's m squared, and then you square it again. All right. So we know that if you carefully analyze this free energy and then ask the simple question whether or not we can describe an ordered phase, yes, the answer will be positive. First of all, we consider homogeneous configurations, assuming that all the gradients of n are 0. We drop this term completely. We're looking at homogeneous in equilibrium state. And then we know that this coefficient A changes its sign across the transition from positive to negative. Once A becomes negative, then for the magnetization M, you obtain the following equation: A plus B sum over J from 1 to M Mj squared. This is a total M squared, which is written here, is equal to 0. There is only one solution. M is equal to 0 when tau is positive. It means that you are above TC. I'm just repeating something you already well know. You know very well. And there is one more solution below TC when your M is M naught. And M naught can be found from this equation. M naught squared is understood in this way. Is minus A, so minus A divided by B. It's alpha divided by B modulus tau. So this is the picture below TC. This is the picture below TC. You do have a transition. Main field always gives you a transition once you have this kind of expression for the free energy. Whatever is the space dimensionality, whatever is the structure of M, you do have a transition. Even in the case where you have only one component, in Ising case, you again have the transition. Mean field is very generous in this aspect. So we are not, after looking at the specific features of this transition, it's a separate problem, quite a complicated problem, especially in dimensionalities below 4, as we know. There is only one upper critical dimension. For the Ising model, it's 4. We don't know what is the upper critical dimension for this model, but believe me, it's a problematic task to solve everything in dimensions 3, 2, or even 5. But we will find out in 1 and 2 there is nothing to solve. So let us follow a different route. Let us ask the following question. Suppose we know from the midfield that below sum to C there should exist a non-zero magnetization, which spontaneously breaks just this symmetry, right? What does it mean? The symmetry is broken. So we understand that this vector, m squared, which is m1 squared plus m2 squared plus so forth, plus mn squared, this is the number of components, right, should be equal to some m0 squared, which is a function of the temperature. It looks like this. M0 is a function of T, this is to C, this is 0, and this is m0 star, if you wish. The upper possible level. So this expression is constrained by a non-zero right-hand side, and what does it represent?
Sphere.
What is the dimensionality of the sphere? N minus 1. Right. It's an equation of a S minus N minus 1 sphere, which mathematicians would denote like this. So if N is 3, if you have a 3-dimensional vector, it's a usual sphere. Right, S2. So your magnetization is defined somewhere on the sphere. Looks in some direction. Now, the natural question is, suppose I'm not looking at the regime when the temperature is much less than Tc, almost 0 if you want. Non-zero T, but very close to it. But it doesn't matter what. What is sufficient just to make sure that the temperature is much less than Tc. Right? What should we have in mind in this case? What is important in this case? Let us look at the situation when the number of components of this vector is not 3 but 2. We have already discussed this picture once. Let us measure here M1, here we measure M2. Let us recall how the free energy should look like in this case. This is what we call a Mexican head potential. So, if I fix some direction, suppose the second direction, M2 direction, and vary M along this direction only, that means that I will go down the slope, reach the minimum, and then go upwards. I will pass this minimum. So my potential will have a local minimum. It's absolutely clear that if I had solved the kind of a mean field problem only for this radial degree of freedom, well, including some inhomogeneous, for instance. So if M is inhomogeneous, for instance, but only allowed to vary in this direction, I will obtain the standard picture that we have for Einstein-centric fluctuations with some characteristic finite correlation length. Because this is precisely what happens below TC. Below TC, if you don't have this fancy potential, your dependence of the free energy as a function of phi, some other parameter. In the Eisen case, below TC looks like this. It has two symmetric minima at phi naught and minus phi naught. So what I'm talking about, it's about this region. It's a fluctuation around the non-zero value of modernization, each of which there are two such things, corresponds to two possibilities to break spontaneously Z2. Here you have a continuum of such possibilities because any possibility along, I have to change the color, along this line, which lies just within the narrow channel on the bottom of this potential is equivalent. So we're quite happy with what's happening in the radial direction. The radial direction, what we learned from the Ising model, the same happens there. But there is a new feature which is absent in the Ising model. This degree of freedom. This degree of freedom reflects the fact that the space of degeneracy of your magnetization M1 squared plus M2 squared equal to some M0 squared is nothing but a circle. So your magnetization is allowed to vary on a circle. It's a continuous manifold, as opposed to 2 points up and down. This is a discontinuous manifold, a discrete manifold, consisting of 2 different points. There is no path, continuous path connecting them. Here we have such a possibility, right? So therefore the question is, if I consider some spontaneously broken direction below to C, and then ask the question, what happens if I take into account the transverse fluctuations of magnetization? Again, if I know that in the radial direction I have more or less the same picture as for the Ising model with a finite correlation length, if I go sufficiently low in the temperature, below TC, I can freeze the radius of this vector. And the only degree of freedom which will remain all in rotation. So the whole dynamic will be only purely rotational. The length of the vector will not be sensitive to anything because the temperature is extremely low. You are close to saturation. Unfortunately, I have removed what was important, and not as a function of T. I'm in this region at T much less than Tc. At T much less than Tc, I don't care much about how the length of the vector varies. It's already close to saturation. But there is this degree of freedom. It's like a rigid vector can still rotate. I'm about this. I'm after this. It's not the change of the length. The change of the length of the vector doesn't bother me much. So therefore, let us exactly do what we're supposed to do. Well, to materialize what I said, to say it more accurately, if you wish, to put everything in formulas which you already know, let me slightly rephrase all these statements and do the following transparent, self-evident, but still necessary job. So suppose I write down my magnetization M of X as its equilibrium non-zero value, plus I add some fluctuation, m small if you wish, which is a function of s, and I will split this fluctuation mx into a longitudinal part and into a transverse part. The longitudinal part means that this is the projection of this vector m on a knot. So m parallel is nothing but, okay, let me put it like this. I have to project everything on the direction of m naught, to put the direction of m naught, and then everything divided by the naught squared. Is it clear what I wrote? This is a vector looking along m naught, along the spontaneous magnetization. This is the magnitude of this fluctuation, which represents a projection onto this direction, and everything is normalized in such a way that the degree of m naught here and here cancel. So this is the longitudinal projection. If I consider now m perpendicular, then perpendicular has the following property. And perpendicular scalar product with m naught is zero because it's just perpendicular. Now you can play such a game. It's very much in the spirit of what is written here. I will now remove this. You may simply assume that, let me consider fluctuations, only longitudinal fluctuations. Namely, let me set m being equal to m naught plus m parallel, and set all the other components zero. No perpendicular components, because perpendicular components would appear at one of these places. I don't have them. If I don't have them, then the free energy, the corresponding free energy for the fluctuations, delta F, would take the following form. It would be ddx. There will be 1/2 c gradient. Okay, again the same story. From I goes to 1, from 1 to d, delta I and parallel squared, and plus 1/2 kappa squared and parallel squared. Just from the standard consideration, when I consider all the quadratic terms, I can discard all the other higher degrees of m, and the structure will be precisely the same. I'm very sorry I didn't write it accurately. It should not be kappa. If I push c outside, then it will be kappa. Let me. No, everything's fine. Everything's fine. When kappa, of course, will play the role of the longitudinal correlation length and will look like a square root of c times the corresponding susceptibility, such that if I calculated the correlation function of the transverse, of the parallel, of the longitudinal displacement, m parallel at x and 0, I will get something like minus x to the so parallel divided by x. In other words, if I had chosen fluctuations to be purely longitudinal, that means this is the Mexican head. If I were only interested in the fluctuations along the radius, I will get this picture, which by its structure exactly coincides with the Eisenstein expansion of the free energy. I want to say that psi is finite. In the longitudinal direction, there is always a finite correlation length, which is not surprising. This mode, we say the radial mode is massive, or it's gapped. There should be a gap at the spectrum. Whereas the azimuthal mode should be gapless, and we'll find out why and how it becomes gapless. So, now, since you know how these longitudinal fluctuations are correlated, you may now always assume that if you choose the regime, the distances, which has much gradient than this, and the parallel correlation length, you can forget about fluctuations, longitudinal fluctuations of your orthogonal. At so large distances, all correlations are completely. The fluctuations are no longer correlated because the length of the vector is frozen, and they are only left with only orientational degree of freedom. So therefore, you are playing the following game. So you can now say that your vector m of x has a fixed length, which is m naught absolute value, times the unit vector n f of x, where the unit vector square is equal to 1, and n of x belongs to one of the infinite points, number of points located on the surface, which is nothing but n minus 1 dimensional sphere. So the only thing, therefore, which is left over, this is your n minus 1 dimensional sphere, which I draw as a 2-dimensional sphere. I can't do anything better than this. So if you started with some direction which you call n naught, which is the spontaneously broken direction, you are somewhere on the surface, you can start wandering along the surface in any direction, changing the orientation of your spontaneous magnetization arbitrarily. This is what you have to do. In case of when n is equal to 2, then there is the circle as 1, and this picture is. Now it's absolutely clear that if I consider fluctuations, I can write down this is a naught. This is some fixed direction, which it's up to us to choose. Can be z, can be x, can be y, up to us. And plus a fluctuation. But now to make sure the fluctuation has to be transverse, let me denote it like this. And here I write down m of x. Under the condition that m of x times m naught is 0. Again, I'm considering only transverse fluctuations. Why? Because what doesn't fit into this category is the longitudinal one. The one which is proportional, which is as a non-zero projection, but I have eliminated such fluctuations. Right? I'm only left with the transverse one. So this is the condition. This is the right form. Why? If I take a square of this, the scalar product this time that is 0. So I have with the square of this and the square of that. Since m naught square is 1, this square is cancelled this square, so you have recovered the right result. In other words, at any point n of x squared, this condition is satisfied. Now you would like to build up delta, the gradient of this quantity. Right? This is a fixed vector. Its gradient is 0. So you have to differentiate the square root, and you have to differentiate this part. If you differentiate the second term, you will get delta I n. If you differentiate this one, this will go into denominator, as you understand, and in the numerator you will have a construction like m dot delta I n. Right? If you differentiate this with the coefficient 2. But this 2 will cancel with 1/2, which comes from the square. The whole thing is that the whole because the whole term, the second term, will be of the second order in this app, whereas the first is linear. Since m is small, I will only consider the case of small fluctuations. I can forget about this. And that replaces this gradient by the gradient of the vector m. And since again all this stuff, all these terms which are present here, only care about the equilibrium value of the other parameter below the c, which is uniform, homogeneous, and have nothing to do with the problem we are after, I can forget about them and replace the free energy by the very simple expression. This will be the free energy of fluctuations. It will depend on m of x, and this is now n of x, all right, m of x, no, m of x is a fluctuation, fluctuating field. It will give me 1/2. If I write down beta and call it s, then I will have here k, 1k is beta times c, which is c divided by t, integral d dx, and here I have, okay, sum over I. This time I would prefer to do it slightly differently. This time I would prefer to write it down like this. I will write down I from 1 to n, and here I will write down delta m I squared. All right. If I had chosen n naught, if I had chosen the other parameter n naught along the x-axis, in other words, if n naught had been chosen as this unit vector with a non-zero component only along the first axis, then I should simply start summing up starting from 2, because it's a transverse vector. It should not have then any component along 1. But since I don't know a priori what is a naught, even though I can assume, I write down all of them, keeping in mind that in fact this is not, this vector has a restriction, has a very strong constraint. It has to be normal with respect to the spontaneously broken direction. Okay. By the way, there are some typos in my lecture notes, unfortunately. Yesterday, again, discovered them, so sorry about it. So, in other words, you can do this in principle, then you will have to start the summation from 2 to n. All right? It's again, it is not principle. What is important is to understand that the vector has to be normal with the direction of the spontaneous magnetization. Once you fixed it, then there's all the other components except for that one. Now, what you do next is the diagonalization of this action or free energy. It's more or less the same. And we know how to do it. We have to expand it into Fourier series. Now, last time I chose this expression, this expansion to be defined in this way. It was 1 over the volume of the d-dimensional space, summation over k, and k exponent e kx, right? Yeah. But nothing forbids you, that perhaps we could have done it, but we didn't. We replaced by square to choose slightly different normalization. Why? Because if you have an expression like ddx m squared of x, right? But suppose you have to take this sum. Suppose. Okay. The square root helps in the sense that it will give you 1 over the volume, because it appears twice. It will give you double sum kk prime. It will give you mk dot mk prime. And that will give you ddx exponent I k plus k prime x. Correct? Now, 1 over the volume times this integral, just 1 of the first power of this volume, gives you a Kronecker. So this is why what you get here is delta kk prime, mk dot mk prime, and the Kronecker. And the Kronecker will, excuse me, plus equal to 0. This is what the Kronecker should be. It will give you mk times m minus k, which is nothing but the sum over k and k modulo square. So you wouldn't care about any other prefactors. These will be cancelled if I had written 1 over v. Then I would be left with extra 1 over the volume, as we were last time. But it's up to your choice. Normalization is up to you. It's a freedom that you are entitled to have. It's a matter of your choice and taste. So let us choose this one. If you choose this one, then using precisely the same derivation as here, with the only difference that you have to differentiate with respect to the coordinate, you will find out that your x is 1/2 of k large. It's not a very good notation. Let be somehow be curly k like this to make it different from the k which is over there. Summation over k. Here you will have. We have to be careful here. Summation over k. K squared. This is for sure. In times sum over I from 2 to n m I k. This is no vector but as a component modulo square. This is how it looks like. Right. Right. So here you have achieved full factorization. It's a direct sum over different values of k and a direct sum over different values of the components of this vector. Right? Oh, full factorization. But by factorization I mean the additive structure of the action or the free energy with respect to all the variables. None of them are talking to each other. They're completely independent, like in ideal gas. Right? So it's a sum of all tissue things. Right? So if I want to calculate now for a fixed value of I is fixed. For a fixed value of I, if I want to calculate the average value of mi k modulo square average, we have done it already, one of the previous lectures. What I will obtain it will be 1 over k large divided by k squared. 1/2 will be cancelled because we remember that since k and minus k here are equally represented, to avoid overcounting, we have to sum over only 1/2 of the variable phase space. This is what I want to do. Now I'm asking the simple question, what is m squared at the some point x? What is the average square fluctuation? What is the average square transverse fluctuation of the autoparameter? we introduce this addition M here as a small extra fluctuation, so it has to be small at all temperatures for this approach to be consistent. How small it is? This needs to be estimated. And all we've done so far was just the warm-up exercise for the final attempt to do the calculation. Now, first and foremost, it cannot depend on x. Because of, can you help me at this point? Because of y m squared x average cannot depend on one coordinate.
Homogeneity?
Yes, yes. Space homogeneity, of course.
Because we took delta.
No, just space homogeneity. It's macroscopically, this problem is homogeneous. There are no extra fields, extra potentials acting on. There is no magnetic fields, local fields, nothing. The space is entirely and completely homogeneous. This doesn't preclude magnetization from fluctuate, but the space is homogeneous. Space is uniform. So therefore, x cannot be a problem here, but if we use this definition, then we will find out 1 over the volume, right? The dimension volume. Some k prime, right? Average value mk prime, vector. This is fine. And the exponent pi k plus k prime times x. But here, what is written? It's only the diagonal parts. In other words, what I have in mind is the following. If I had calculated mik prime using this action, the result would look like it would be delta k plus k prime 0 times this result, times this result, mik squared. Is it clear what I'm writing? Every time your action or free energy is fully factorized, it represents a sum of independent contributions. It's clear that correlations between two values of the fields labeled by k are only non-zero if the sum of these two k's is 0. In other words, if there is a sum m here, this should be its conjugate, such that the average value will only depend on the modulus square. This is the structure of the theory that requires that. It's not me, it's the theory itself. It's the symmetry, the general symmetry. So therefore, here I have only one possibility left, is 1 of the volume, sum over k, and modulus mk squared. As you can see, this term disappears, which means that instead of x, I can put any, for instance, I can take the origin, for instance. The x is not a parameter because of the homogeneity. That's already a result, so we can write down the results now in a very compact way. I will pass now from summation over momentum to integration. And then I will find out that the average m squared of x is what? Is sum dk divided by 2 pi to the power of d, right? And now I would like to take into account the fact that what I have here, that's a vector. For I fixed, this is the importance. The result will give me n minus 1 divided by this large K. And here I have 1 over K squared. The n minus 1 comes from the fact that the transverse component is defined in the tangent space, in a space which is by 1, has less dimensions than the overall space, right? If you had a circle, you would have a point, right? The point means the tangent space. In other words, the coefficient here is an n minus 1, which means that if I had a vector consisting only of one component, that will be a scalar. That will be something like an Ising model. And the right-hand side would disappear immediately, and n minus 1 would vanish, which would means that what I'm doing doesn't make any sense because there is no continuous group. There can be no continuous symmetry for the other parameter for magnetization, which has only one component. It's a scalar product, scalar quantity which cannot rotate. There is no angles in one dimension. Right? So this is why n minus 1 is not terribly important. It simply gives you a correct prefactor. What is important is inverse k and the integral, which is here. Now let's do this integral very roughly. I will skip this and I will skip this. You can keep it, but I don't want to deal with something which doesn't bother me much. It's 1 over k. Why I care about this k? Because this is the inverse temperature. So 1 over k is just the temperature itself, roughly speaking. Now I have to integrate d dk, everything is isotropic, the angles will be their contribution expressed in terms of gamma functions, I don't care. So basically it's k to the power of b minus 1 dk, right? So the radial part. With this extra k, I will have k to the power b minus 3 dk now about the limits of integration. So the upper limit is no problem. We know that there exists the maximum value of your momentum in any model. It is inversely proportional. The cutoff length, minimal length of your problem. What is that? Radius constant, for instance. Or the radius of the interaction between the neighboring spins. The minimal microscopic length, which in condensed matter physics always exists. This is a problem for high energy physicists. They don't have this covered. We do. So therefore, this is 1 over the A naught. Sometimes it's labeled by lambda. In my lectures, it's the upper momentum cutoff is called lambda large, which is roughly inversely proportional to the microscopic length. Right? Much less trivial in condensed matter physics is the minimal length of your problem. Much less trivial. Of course, from general statements, quite generally, you would be inclined to write here 0. Because, well, if you do radial integration, you start integrating from 0. Be careful. This is not always possible. Roughly, if you have a sample whose linear size is L, you remember how the momentum is quantized in a finite size sample whose length is L. It's 2 pi over L times some integers. So the minimal value of L in that nomenclature is 1 over L, 2 pi divided by L. Why not 0? Because 0 is something counterintuitive and non-physical for a finite sample. K equal to 0 means that infinite length, infinite wavelength. Such waves don't exist in a finite size sample. So therefore, as a minimal value of K, you take the minimal allowed by quantization, allowed value of momentum. So therefore, this minimum of K is roughly 1 over L. But of course, here is the main point. We are talking about the average quantity for a system which underwent phase transition. So this is something which is supposed to be sustainable with respect to to the passage or to the thermodynamic limit. So you have to have in mind that in the end of all calculations, you have to send L to infinity to make sure that your theory is sensible and is correct, is meaningful. If it is not, if you get some kind of divergences, as we will see, this is indeed the case, then we have a major problem. We have to change, reconsider, revisit completely our approach and say something new and different. So what we see here looks like as follows. It's 1 over this k parameter. It is 1 d minus 2. The upper limit is k maximum. Let it be lambda to the power of d minus 2. And let it be k bar minimum. Minimum to the power of d minus 2, which I will rewrite as lambda here, d minus 2. Excuse me, 1 minus the minimum length, k minimum, divided by lambda, everything in the power of d minus 2. Is it fine what I wrote? Yes. That's correct. That's correct. Fine. So what we see here, what we observe here is the following. If the space dimensionality is greater than 2, it's 3, 4, or higher, conclusion number 1, D is greater than 2. Physically, three-dimensional thing. So then this degree is positive. This power is positive. Then you can freely send k minimum to 0. You could blindly send L to infinity. Because everything just goes to 0. And you remain with a finite expression. Everything is finite. Which is most important, 1 over k is proportional to the temperature. So if the temperature is small enough, m square average is also small enough. So the lower the temperature, the smaller is the average square transverse fluctuation. Approaching 0 temperature, you kill all these fluctuations completely, and you are left with long-range order, which is quite stable against these fluctuations. Why? Because the average m squared vanishes. You wanted to ask me something? No? No. Okay. So we write down there exists long-range order. It is stable. Long-range order is stable against transverse fluctuations. Now we go to the case d equal to 2. Well, you immediately can anticipate what happens when d goes to 2. You have an uncertainty, 0 here and 0 here, but it's much better to go down to look directly to this. When d is equal to 2, you have this dk divided by k. So what you have in this case, when d is equal to 2, your m squared is proportional to the temperature, because 1 over k gives you a temperature, times the logarithm of the lambda divided by k minimum, which is beautifully diverges when you pass to the infinity thermodynamically, because k minimum goes to 0. At any finite temperature, except for the temperature is exactly 0. When the temperature is exactly 0, you take this limit first, you get 0, and then you can do with this whatever you wish, because it doesn't exist anymore. But if temperature is finite, With these coefficients being finite, this logarithm tends to infinity in the thermodynamic limit. And m squared diverges. Let us continue discussing low dimensionalities when d is equal to 1. It's clear to see that m squared is proportional to t, simply L divided by k minimum. With again the same conclusion. You see? Even stronger, because this divergence is stronger than the logarithm one. Here at least you can find such a length, if you look at the value of the minimal momentum, that for a given temperature, m squared is still not too big, not too large. So at some distances, you still have more or less quasi-long range order. That's indeed is the case, by the way, in two-dimensional systems. Two-dimensional systems are very special, we must have special lectures. But in 1D, you are lost immediately. The conclusion is, in lower space dimensionalities, in 1 dimension and in 2 dimensions, in these 2 dimensions, what in 2? Long range order of a system possessing continuous symmetry, I emphasize continuous symmetry, is eliminated at any finite temperature. By what? What is the source of this?
Entropy.
No. The source must be dynamical. The source follows from this structure, k squared in the denominator. Just, you understand what's going on. It's all about this extra continuous degree of freedom in which the older parameter explores the manifold of all its values which are degenerate from the point of view of free energy. Of course, it's Goldstone modes. This is just because that in the continuous case of continuous symmetry, the order parameter in the ordered phase, when it starts fluctuating in the transverse direction, it can explore all these possibilities. And the corresponding zero modes, what is meant of Goldstone modes? They have a zero energy. Actually, what is written here can show that it's a square of this energy. They do this destructive job. These fluctuations are so easy that in low dimensions, it's enough to have them to destroy everything. It's clear that if you could freely rotate your order parameter, the average value will be strongly decreased and maybe even disappear. So this should not come as a big surprise, because we know that low dimensionalities is a serious thing already for these systems with the discrete symmetries. We know that in discrete symmetries case, the Ising-like models in 1 dimension are never ordered at finite temperature. That is all. It's the Landau-Piles theorem that we already discussed. Continuous symmetries are much more powerful because they destroy easier. It's harder to destroy an Ising model because only 2 directions, up and down, and there is a gap separating them. Here there is no gap whatsoever. You can go smoothly from one to the other, along this curve, along this surface, along this circle, in case of the XY model, or the sphere, in case of 3-dimensional magnet, and this is exactly what kills your ordering at finite temperature. This is the content of the Marathwada theorem. It forbids long-range ordering of 1-dimensional systems with a continuous symmetry. Doesn't matter what kind of continuous symmetry. The group may be O2, O3, O25, or some other continuous, millions of any Lie group, any. The long-range order doesn't exist. Yeah,
you said about this continuous symmetry, and before, like sometime you also talked about some symmetries are more stronger than other symmetries. For example, ON is stronger than G2. So we have seen that in this case, the D, the dimension for having the order, like long range order is 2, which in previous case was 1, in easing case. So
it's easier to
yes,
kill long range
so
order. Yeah.
if we see some other stronger symmetry, I don't know right now what the
No.
is. Will it go up and down?
No.
G.
I understand your question, but please be consistent with what you are asking. I said all comes to the identification of the so-called space of degeneracy of the order parameter. What is the space of degeneracy? It's some kind of the manifold of allowed values of the spontaneously broken, of the magnetization of the order parameter, which characterizes the spontaneously broken phase, for which the free energy takes the same values. In other words, if my order parameter varies on some manifold, it are just 2 points in case of Ising model, up and down. It is a circle for planar spins, it's a sphere for three-dimensional spins, and so forth and so forth. If I have identified all this, then I can classify them in the following way: continuous or discontinuous. Any discontinuous symmetry, not Z2 is not the only option. There may be Z3, Z4, it may be more complicated things. It might be some stars, triangles, whatever the discrete symmetry of a square, of a cube, the cubic lattices exist. Every time you deal with discrete symmetries, when the other parameter takes finite amount of allowed values separated in the energy space by energetic barriers, then the critical dimension is 1. In one-dimensional system with such a discrete symmetry, long-range order doesn't exist. In higher, it does. Now, when you replace this discrete symmetry by any, I emphasize, any kind of continuous symmetry, because the Marathwada theorem, which tells that this should exist, the corresponding, conserving quantities, precisely in the same spirit, this Marathwada says that as long as the order parameter varies continuously on some manifold, like a sphere, like anything else. There are many continuous manifold topological spaces, for instance. They should exist. The so-called collective modes, called the Goldstone modes, according after Jeffrey Goldstone discovered them, whose excitations, just exciting such modes, would mean you would like to change continuously the direction of your magnetization on the surface. This is why I'm asking, what eventually kills the order parameter in 2 and 1 dimensions? And here, the very possibility of the magnetization to travel on the surface. And this is exactly what the Goldstone modes are about. So the Goldstones kill long-range order in 2 and 1 dimensions. So this is precisely what the theorem says, and it doesn't matter much. In principle, doesn't matter at all what kind of continuous symmetry. Any. Just any. That's it. All right. Any questions here? Now we are preparing to go into in-depth in the details of the phase transition beyond main field theory, which will be a harder thing to comprehend. So I expect that you will ask me much more frequently than you do now, because the subject is quite complicated. So I'm trying to introduce you to the basics of the so-called scaling theory of these transitions. We already know that mean field not always is correct. And if mean field doesn't work, the question is how to describe the phase transition. But we frequently said several times that it's all about fluctuations, which are neglected within the midfield approach. Well, you may say if you incorporate homogeneities, then you will replace the Landau expansion by the Gisborg-Landau expansion, which contains the gradient term. The rest is still there. It's not as much as to adding the gradient term. It's about the way we treat the fourth order term. We didn't pay much attention to this term, the B term, remember, the one at which the order parameter appears in the fourth order. It turns out that that's precisely the moment when many unexpected things are uncovered and new physics emerges. This term plays a very important role. Why? Because, as you remember, let me write it down again in the way we write down the action. It is some S naught, which doesn't matter much, the integral over space. Here we have some C bar. Now, previously I wrote K, but I can write C bar. C bar will be beta C, B bar will be beta B, and A bar will be beta A. Gradient term, let me write down eta here. Square plus A by 2, eta squared, plus B by 2, eta to the fourth. So, let us get directly to the critical point. Remember, tau is equal 0, A bar is 0, and you are left with this term and this term. Gradient eta squared plus eta to the fourth. So your potential, this is the potential part, right? U as a function of eta, which was more or less quadratic in the presence of this term, transforms to phi to the fourth. And here it is almost flat, if you wish. It's the fourth order. So the first derivative vanishes, the second derivative vanishes, the third derivative vanishes. So everything vanishes. The third doesn't vanish. So this is not a Gaussian model. The Gaussian model would be this plus this. Or if I am below TC, I could solve first for the equilibrium value for eta below TC, and then expand with respect to this average value. And again, we'll get something like a Gaussian. Now, why Gaussian versus non-Gaussian? This distinction is important in statistical physics. It's very, very fundamental question, by the way. If you have some physical quantity phi, not necessarily, just forget about phase transitions. You have some thermodynamic quantity, which in real space, they take values depending locally on the coordinate, and which at equilibrium spontaneously in the uniform space takes some uniform non-zero value point, like density, for instance. You take a density fluctuates from point to point, But there is a notion of average density at a given temperature. So what you know about it, you know the following, that so if your free energy as a function of this phi, let us for a second forget about spatial inhomogeneities, consider only homogeneous configurations. Then we can talk about free energy as a function of this field. Then we know that to find the equilibrium value, we have to solve this equation under the condition that the second derivative is positive. That means that this solution, phi equal to phi naught, is a minimum. Is a minimum of f. If this is so, then of course you are forced to assume that it has to have a form with A positive. Don't forget, don't think in terms of phase transitions. You keep them in your subconscious. So consciously just think of any thermodynamic quantity that you may have. It fluctuates. This is how the uniform fluctuation should be described. It has to have such a form. In the vicinity, close to equilibrium. At small deviations from equilibrium, it has to have such a form, because just after performing all these procedures, I will get phi is equal to phi naught. This is the solution of this, and this tells me that A is positive. Now, if I allow the field phi to be weakly, slightly inhomogeneous, then I have to include the non-zero contribution to all these inhomogeneous into the free energy. And therefore, the free energy will transform to a functional, and the whole expansion will take the following form. It will be an integral over space. Here I will write down something like this, and add what I already have. Of course, it is understood that phi is a function of x. Minus phi. Nothing else. So it's again a quadratic form, and it's again a Gaussian model. So the Gaussian nature of the free energy for a fluctuating quantity in thermodynamics follows from the very simple requirement. The realization of this fluctuating property of quantity should correspond to the requirement of equilibrium. At equilibrium, the free energy must reach its minimum. That's it. Nothing else. Right? But now, with our experience in dealing with functionals like this, we immediately conclude that the fluctuation, so let me now introduce phi of x as phi of 0 plus delta phi of x, which is a fluctuation. I measure now phi from its average value. In this case, it will be transformed to delta phi squared. In here I will have simply delta phi squared. Why? Because the average value of phi naught is homogeneous. If I now look at the correlations, we have done it already. That will be proportional to minus x to the power of exponent divided by x to the power, if I'm not mistaken, for the d-dimensional space. It's an exercise for you to show that Oh, where is it? Show this over here. It must be d minus 1 divided by 2, right? Check if it is correct. When d is 3, then we have the power is just 1 here. This is what we had calculated using the Green's function, you remember, right? But in general case, you may be interested in finding out just for curiosity. Which power is here when the space dimensionality is different. All right. So, what is psi? Psi is, of course, the correlation length. Why psi is finite? I emphasize, for a normal equilibrium phase of any statistically meaningful system. Because A has to be strictly positive. Therefore, the quantity, the ratio C divided by A is finite. So therefore, the correlation length is finite, because it's expressed as a square root of that expression, the ratio. Right? So the correlation length is finite because the system has to be at equilibrium. The phi has to take some equilibrium value, non-zero equilibrium value. And this is why we can divide our system into subsystems with a linear size L, less on the order of psi, separated by distances much greater than psi. This is what is meant in statistical physics, that let us first consider a subsystem and then take into account the environment in some way. The very fact that you can decouple your system into subsystems or single out the subsystem and treat all the rest as a kind of environment. It assumes that this is possible. And this is possible because of the fact that psi is finite. So there is a characteristic length, you can go beyond that length, that scale. At larger distances, you lose our information. And these subsystems are statistically independent. Statistical independence and distances x much greater than psi follows from this formula. This phi belonging to this and this two subsystems are uncorrelated because the distance x separating them is much greater than psi. So this is the role, the fundamental role of the correlation length. Now we are looking back to this formula. We go back to the problem of phase transitions. So again, the possibility of dividing your system into subsystems and the claim that the distribution, the functional describing distribution of physical quantity in terms of the Gaussian model, the Gaussian kind of distribution, are synonyms. It's just the same statement. Any normal system at equilibrium is described as fluctuations in any system at equilibrium can be described in terms of the Gaussian model, except for special cases when such system undergoes a phase transition, continuous phase transition. Then psi goes to infinity, all the length becomes equivalent, and you can't do anything. The old statistical physics no longer is operative. It doesn't work. You need something different. Why? Because you can see that when A goes to 0, then you have this. This is very nice because here we also have it. But I'm sorry, here we have delta phi squared, here we have e to the fourth. It's a completely different story, I'm sorry. You can't do anything. You can't even do this integral, exactly. You can't do this integral. Which means that you face a major problem. of taking into account all length scales of the same way, in the same framework. And it needs to be done in a consistent way. It has been done by several outstanding physicists. Perhaps in this list I should first put the name of Leo Kadanoff. And I don't know, many others, but perhaps one more is Kenneth Wilson. Yeah, and many others, but these two, in my opinion, have played the major role. So next time, therefore, we will start the scaling theory of phase transitions. Be especially attentive, and I'll try to ask good questions because it's a complicated stuff. We will start something absolutely new approach to the problem. You will start probing something, elements of quantum field theory, or theory of phase transition. You will find out what theoretical physics is about these things. All right? Any questions? No questions. Yeah, I will perhaps for the next lecture, I will inform the ladies the diploma course. I will send them extra notes on the scaling theory, because what is given in this bunch of notes is not quite what I'm going to discuss with you. It is more or less the same, but not exactly. So I would prefer to deal with it much. All right, see you then.